Hello. In today's class, we're going to be covering a brief introduction to R. We have three main goals for today's class. One is just to talk about what R is and why we're choosing R for this course. And then we're going to go over some basic data types in R and some of the key things that you'll need to know with each of those data types. And thirdly, we'll just discuss an introduction to RMarkdown, which is the primary way that we'll write R scripts in this course. So R is a computing environment and programming language that's primarily designed for programming with data. And it's built for interactive style of programming, and therefore it has really great tools for working with and visualizing the data that you are computing on. It's based on the S language, which was developed way back in the day at Bell Labs. And there are a few different flavors of R. Three of the most common are base R, tidyverse, and data table. In this course, we'll be using primarily tidyverse. If you want to get R on your own computer, you can download R from the CRAN website. And then it's really easy to start on the command line with just typing R and enter. But that doesn't give you a graphical interface, and that's way easier to use with GUI. So we'll be using RStudio in this course. And there are two primary ways to get packages installed in R. One is from the CRAN repository with install.packages, and the second is from Bioconductor, which I'll talk about a bit more in a few slides. Okay, so why are we using R over Python or Matlab or C? One is that R is open source software, which is really a pro over Matlab, for example. And secondly, Bioconductor is a repository of computational biology packages. There are over 1,800 packages, and it's such a standard in the field that often people will publish their computational biology analyses or packages as R packages in Bioconductor. Thirdly, RMarkdown is a really nice way to do literate programming where you're writing plain text explanation of your code in line with the actual code that's doing the work in a version trackable way. Jupyter Notebooks also does this, but it's less able to be version tracked. RStudio is also a really nice piece of software that allows you to make good looking figures in a reproducible way. And lastly, R indexing is one-based, which makes a lot of intuitive sense. So if you want to check out some of the figures that you can make in R, there's rgraphgallery.com, but suffice it to say for now that almost any figure you can think of, you can easily write some R code to make that figure. Okay, so let's just dive right into R in RStudio. For those of us in the class, we'll be using fiji-viz.colorado.edu/RStudio, where an RStudio server is already set up for us to use. So I'll navigate there now. You'll just sign in to the RStudio server using your identity key and password. And just to familiarize you with the window that you're seeing right now, on the left, we have the console that's running R. This is the same thing you'll see on the command line if you just run R from the command line. And this is where we can run our code. On the right, you have two windows. At the top right now, it's showing an environment window, which allows you to view the variables that are loaded into your environment. And on the bottom, we're seeing the files browser, and it opens up first to your home directory. So the first thing we'll do today is start a new R project. We can do that by going to the upper right project selector, selecting new project, create a new directory, and then we'll call this project first R project. Okay, so now that we have a project set up, you can see that R has automatically changed us into the project directory called first R project. And we see there's just a .rproj file there and nothing else. So the first thing that we'll do now is create a new script. You can go to the upper left corner where the new file icon is and create a new R script. That gives us a fourth window over here, which is the scripting window. And that's where we'll be writing all of the R code. And then we can send it down to the console with a control enter. So first, let's save this file. We'll call it first R script. And R files are named with a .r extension. You can see it automatically put in that extension. Okay, so let's get right to it and create a variable with 100 random numbers in it. To do that, we can use this rnorm function, and we'll just say we want 100 random normal numbers. So I'll press Control Enter to send it down to the console, and then it populates in our environment window. We can see we have a new variable named x that is length 100. So there are a lot of built-in mathematical functions in R. For example, we can just take the mean of x or find the range of x, or we can create a histogram of these numbers really easily. This is just an illustration of how easy it is to get to figures in R. That was just 3 lines of code. So let's talk a bit more about our objects. So primarily what we're doing when we're working with data in R is manipulating objects. And each object is going to have a name and a type associated with it. When we're naming objects, case matters. So lowercase x is actually a different variable than uppercase x. And the preferred naming convention is all lowercase with underscores in between the words. And variable names must start with a letter. To review these and other style guide recommendations, you can go to style.tidyverse.org. And finally, you may have noticed that to assign the variable x, I didn't use an equal sign, but rather I used this left caret followed by a dash. So in R, that is the assignment operator. The equal sign also works, but what does it really mean for I to be equal to I plus 1? Because of that awkwardness with the equal sign assignment operator, R has chosen to use the left caret dash assignment operator. So now we'll talk about some basic variable types in R. Numeric is the main variable type for numbers in R. In other languages, this is called floating point or double data type. You can check if a number is a numeric type by using the function is.numeric. R also has a type for complex numbers. And there are a few special values to be aware of. NA stands for not available. You'll see that often when there's missing data. NaN is what happens when you divide a number by 0. And there are numbers that represent positive and negative infinity. Null is something that you'll encounter when you see a list of length 0. And you can check if something is null by using is.null. So vectors are another very basic object type in R. And actually, when you have a single number, in R, that is a vector of length 1. Some operations work element by element, while others operate on the whole vector. And that's function by function, but it's something to be aware of. And you can generate vectors of regular sequences using the seq function, the rep function, and you can also just have a colon in between two numbers to print the whole range of numbers from, for example, here 6 through 56. And then integer is a whole nother type, and I'll talk about that now as we go back to R. Okay, so let's create some numeric variables. I'll just assign 1 to x, and we can ask, is that numeric? And is it an integer? So we find that x is indeed numeric, but it is not an integer. To create an integer, we have to append an L, capital L, after the number, which will create an integer. An integer is also numeric, so both of these will give true in this case. Okay, so let's check out that nifty seq function where we can specify a range of numbers, let's say from 2 to 30, and we'll do every 3 numbers. So now we can see we have 2, 5, 8, 11, 14. And if we want to create a range of continuous numbers, we can say 2 to 30. And that gives us each number 2 to 30 inclusive. Okay, let's define a vector using the C operator. So C is for concatenate. We'll call this vector peak sizes. And we'll concatenate 3 numbers together. And now we have a vector peak sizes of length 3 with 10, 80, and 300 in it. We can check the length of this vector with length, peak sizes, and we see that the length is 3. We can also append more values to this vector, also using this C operator, where we'll just put peak sizes as an argument in concatenate and then add on some more values. So now we have a vector of length 5. So as I said, some mathematical operations operate on every value, every element of the vector, and we'll check out a few of those. So square root, for example, just sqrt, will square root each value in the vector. Log, similarly, will give you the log of each element in the vector. However, if you use min or max, that operates on the vector as a whole, and it will return one number, which is the minimum value, or the minimum element in that vector. Okay, a common thing that you'll have to do with vectors is access subsets of that vector or individual elements of that vector. In order to do that, we can use indexing. So in order to get the fourth element of peak sizes, we use square brackets, and then we can access just the fourth element, and we can see that that corresponding fourth element is 2 here, and that's what's returned down here in the console. So we can access also multiple values, again using this C operator to create a vector. So let's return the second and fourth value in this vector. It's also helpful often to use this colon syntax to access a range of values in your vector. So let's access the first through the fourth element. You can also set elements of a vector using indexing. So we'll set the fourth element to a different value. Let's set it to 10. And it's worth noting that if you have multiple values selected, so here we've selected 3 values, that whatever is on the right side will be repeated enough times to fill up the number of slots that are on the left side of the assignment operator. So here we're setting the first 3 elements in the vector all to 10. And we can see if we print peak sizes now, the first 4 elements are now 10. Okay, you can also index by name. And in order to do that, we need to set some names of this peak sizes vector. So right now, if we access the names of peak sizes, we get null as a response since it is a list of length 0. But we can now name these peak 1, peak 2, peak 3, peak 4, peak 5. Okay, so now if we access the names of peak sizes, we can see that the names pop up, which also means we can index using the name. If we just want peak 2, then it will return to us peak 2. Now, of course, the name that you type there has to match one of the named elements exactly. And in general, this is a good thing to do because as you're modifying vectors, the position of the vector may change, and it's a bit more readable and robust to refer to elements by their name. Okay, so that is a brief introduction to vectors. And there are tons of cool functions that you can use with vectors. I've listed them here in the slides just for reference, but there's a ton of things that you can get: the standard deviation, the cumulative sum, the cumulative product. This will be here for reference in the slides. Okay, so matrices are another basic data type in R. A matrix is a vector with some additional formatting in order to mold it into rows and columns. And this is not something you need to know necessarily when you're starting out, but these matrices are stored in column major order, which means that you can index into them using a single number. And if you wanted to get the 9th element, that would correspond to this 3rd row and 3rd column in this 3x3 matrix. To construct a matrix, you use the function matrix, or you can use cbind to bind 2 vectors together in a column wise, or rbind to bind 2 vectors together row wise. So let's go back to our and check out some matrices. Okay, so I'm going to create a vector that is just the numbers 1 through 6. And we can ask R, is this a matrix? And we get the answer false. But in order to turn it into a matrix, all we have to do is set the dimensions of this matrix. And let's set the dimensions to have 2 rows and 3 columns. So now if we print X, we can see that it is now in matrix format. And we can ask again if this is a matrix, and that returns true. Okay, so to access elements of a matrix, to index into the matrix, we again use the square bracket notation, but since we have 2 dimensions now, we can put in 2 numbers. So if we want the second row and second column of the matrix, we can put in 2, 2, and that will give us the element in that row and column. So as I said, we can also just index using a single number, since it is ultimately stored as a vector in R. And we can slice the matrix by giving it multiple rows and multiple columns. So here we'll return this sub matrix. And it's also useful to note that by leaving a column or row entry blank when you're indexing, that it will return all of the rows in this case. So if we just want the third column, but all of the rows, we can do blank, 3, and that will return just the third row. So when it returns this value to us, it is no longer a matrix. It's instead just converted back into a vector, but you can use the parameter drop equals false if we, for example, wanted to return this in matrix format. So now if we ask is.matrix, it returns true. Boolean values are another basic data type in R. So that's just true or false, indicated in R by all caps true or all caps false. You can abbreviate them with a capital T or capital F. And they're equivalent to 1 and 0 respectively. So you can coerce a true into an integer with as.integer, and it will return 1. So there are, of course, all of the Boolean operators that you would typically see with the Boolean logic. So an ampersand will return true if both A and B are true. There's also a double ampersand operation that will only evaluate the first element, A, and if that is true, it will evaluate B. But if A is false, then the whole statement will be false, so it shortcuts and doesn't evaluate B. A not is indicated by an exclamation point. And finally, a double equal sign will allow you to compare 2 numbers. It's worth noting, for reasons that we won't get into here, that you really should use the function all.equal for numeric values and double equals only for integers. So let's check out some Boolean values. One use for Booleans in R is to index into a vector. So let's rewrite our X to be values 1 through 10. And if we say X greater than 5, it will return to us a Boolean vector where all of those values that were greater than 5 are true, and all those that were less than 5 are false. And this means it provides a convenient way to index into vectors where we can say, give us only those values which are greater than 5, and it will return just those values. So it's worth noting too that the which function will allow you to get the indexes of those values that are true. So which will only give us the indices of the elements that met that criteria. In a way, which turns Boolean into indices. So let's construct a little bit more complicated Boolean logic where we want just the middle of this vector. So let's say we want X greater than 3 and x less than 7. So you can see this gave us now a vector where there are just 3 trues in the middle, and we can index using this variable. It will just give us 4, 5, and 6. You can also negate this with an exclamation point, and then it will give us all of those that are not true. To illustrate that more clearly, let's just have the not sign in front of the middle, and it will give us the inverse of that Boolean vector. Okay, lists are another basic data type in R, where you can collect objects of different sizes and types. And lists are often used as the return output of a function so that you can have all of the relevant information for that function in one object. This is because functions can only return one object. We'll talk more about that later when we talk about functions. So similarly to vectors, list elements can be accessed by name or by position. So we'll talk in a bit when we go back to R about what double square brackets versus single square brackets mean. But in brief, double square brackets will give you the element residing at that position in the list, and single square brackets will give you a list containing that element. Okay, let's create some basic lists. This one we'll call gene info. And we can have in this list an ID, a name, and a biotype. So if you'll notice here, I am naming the elements of the list as I'm creating the list. So this can be accessed, again, either by the position in the list, or we can access it with the name of that element. One other way of accessing elements in a named list is that we can use a $sign. And the nice thing about the $sign is that it will autofill the available named elements in that list. So that makes it really easy to autocomplete. Let's say we want the biotype here. So you may have noticed that in the environment window, gene info shows up in a different category than the rest of the vectors that we've made. And it has this little blue icon next to it where you can expand that object and examine some of its properties here in the environment window. So you can see here that this list contains both a numeric element and 2 character elements. We can change it back into a vector by using the unlist command. And when we do so, because it's changing it back into a vector, and a vector can only contain one type of data, it's coercing our ID, which is numeric, into a character. So that's why it has quotes around it down here.
So that's actually a nice segue to talk about our second to last basic data type in R, which is strings or characters. So a character array is just a vector of strings. And you can use single or double quotes, but you can't mix them together. And backslashes allow control characters such as \in, which is for a new line, or \t, which is for tab. Okay, so let's create some characters here. So as I said, you can use double quotes, but you can't, for example, start with a double quote and end with a single quote. So what you see down here is that once you've run this command, it's expecting the matching ending quote, and it gives you a plus sign to allow you to complete the command. So if you see this down in your console, then one way to fix that is to just match the quote. So we'll add one more quote down there, and then it will give us the right caret, which says that the console is ready to take a new command. Okay, so that's an example of what we don't want. So we can use this command cat, which is based on the same cat that we saw in bash, to print messages in your script. So if you are going to say, now we're iterating over our DNA binding proteins, that will just print that out to the command line. And that's useful to use in the middle of a script when you want to write a message. If it's a long-running script, that can be quite useful. Also, in the middle of a cat command, you can insert a variable. Let's say we want to print a message that tells us which DNA binding protein we're running. So let's set x to be HDAC3. Then we can say cat now running x. And then we want a new line. We can create a character with the \n that will give us a new line at the end of that line. So paste is a really nice function when working with strings that allows you to put variables and characters together into one character. So as an example, let's say we want to create a bed file named after this variable, which is now containing HDAC3. So we can say paste, and our first argument will be our variable, and our second argument will be .bed. And in fact, here, the default separator for paste is a space. But if we use the paste0 command, the default separator is nothing. So now we've created a file name. Okay, to further explore strings and characters, let's create a character vector with some DNA letters in it. In order to know how many letters are in each of these characters, we can use the command mchar. This will operate element-wise and tell us how many letters are in each character. We can also extract a substring. Let's say we want just the second through fourth letters in each of these strings. We can use the substring command and give it the starting position and the ending position of the substring we would like, and it will extract out just those letters of our characters. Also, just as in Bash, we can use grep to find matches of characters in these strings. So let's say we're looking for a TC. The first argument is the pattern that you're looking for, and the second argument is the character vector. So here it's saying we found a TC in the second and first element. You can also use all of the regular expression patterns that you can use in Bash. So if we wanted to look only at the beginning of the string and say, find me an AT only that's at the beginning of the string, we can use this syntax here. And even though there's an AT in all three of these, it will only return the match for the first one since the AT occurs at the beginning of the string. Finally, if you want to change your characters to lowercase, you can use the command toLower, which will make these all lowercase. Often when you want to match strings across different data, toLower is a really useful command because R will not match characters that are uppercase and lowercase. So standardizing them can be quite useful. The final basic data type in R that we'll cover are factors. So factors are used for representing categorical variables. Internally, R represents the factor as a numeric value. Let's say our categories are short and tall. Short will be represented by 1, tall will be represented by 2. And this is useful because if you have a really large array of character vectors, it takes up less space to store numeric values than it takes to store character values. It's also really useful for regressions. It's a bit harder to work with sometimes than character types. And for that reason, when we're reading in data, most of the time we want it represented as a string rather than as a factor. So usually at the top of the scripts, you'll see option strings as factors equals false, which sets the default that when data is being imported into R, that it will be imported as strings instead of being converted to factors. Let's create some factors now. Let's say we have a category of our Chip-seq assays. Our categories will be TF and histone mark. and input it. So right now that's a character vector, but we can easily turn it into a factor by using the factor function. And you'll see that now in our environment window, IP category is a factor with 3 levels. And you can see the numbers that each level is represented by over here on the right. If we want to see what the levels of the factor are, we can use levels. And it gives us those 3 levels. You can also change it into an integer, and this reflects how R is actually storing this variable. It's often useful to order your factor. By default in R, the factor levels are sorted according to their alphabetical order, but often your categorical variable will have some natural ordering to it, and then in those cases you would want to specify the order of your levels. So let's say we have a categorical variable describing the size of something. Let's say small, large, and medium. If we turn it into a factor, we want to specify the order of the levels, and we can do that with the levels parameter. So the ordering here would be small, medium, large. Oh, I forgot a parenthesis, so we'll add it in down here, and then add it here as well. Okay, so in a way, we saved the best for last here. Data frames are a composite object in R that allows us to store values of different types in a special kind of list where all elements of the vectors are the same length. So it's like a matrix in that way, but each column can be of a different type. It's super useful for tabular data, which we'll be using a lot, like bed files and CSV files. So a data frame is the base R object, but other R objects that emulate data frames are tibble from the tidyverse and data.table. They're often interchangeable with data frames and can be coerced into data frames. Many other object types can be converted to data frames, and since data frames are so nice to work with, often we will convert objects to data frames before manipulating them. And the function to do that is as.dataframe. Okay, so let's create a data frame now. In order to do that, we'll just create a few vectors here. Okay, so now that we've created a few vectors, we can combine them into a data frame by using the data.frame function. And we'll call this data frame peak_df, just indicating that it's a data frame. Each column in the data frame can have a name, so we'll call the first column names, the second column heights, and the third column in gene body. So when we run that, we see that a new object has been populated in our environment called peak_df. And it also has this blue dropdown where we can see what the object types are of each column in that data frame. I'd like to introduce also this nifty way of examining objects in your environment where you can click on the object name and R will open up a browser where you can see in tabular format the values inside each column of this data frame. Similarly to lists, if you'd like to access a column of this data, you can use the $ to access a named column. So let's say we want to get in gene body out of here. So that's if we want to access a column, but if we want to access a row, similarly to matrices, since these have 2 dimensions, we'll be putting in 2 numbers. So if we want to get the second row and the first item in that row, We can use that syntax if we want the second row, but all of the columns. We can just leave that second spot blank. So that's just a brief introduction to data frames, but you'll be getting quite familiar with them as they are the most useful object in R. Okay, finally, just a final note on objects. Objects are both variables and functions in R, which means that you can use the same name for an object and a function. This is important to note because you can actually write over R functions if you use the same name as a named function in R. So if you don't want things to be confusing, try not to name things that are going to overlap with functions that you know about in R. For example, don't name something sum. So we've introduced just the basic data types here, but it is possible to create your own custom object in R, and many packages will do this in order to fit the type of data that they're generating. And we will see that soon with G-ranges and I-ranges, for example. Okay, I just want to briefly cover how to learn a function that you haven't seen before in R. One way is to use the help function, which will bring up the help page for that, or just question mark followed by the function name. You can also see what the arguments are, or examples, where you can search a function if you're not quite sure what the name of it is. And demo is a really cool way of seeing what is possible with a function. So as an example here, I'll just use question mark hist and run that to bring up the help window. So in this help window, the hist function has been brought up, and we can see all of the arguments that it is set up to take with an explanation of those arguments. And then really usefully down at the bottom, you can see some examples and copy and paste these examples to run them. And then it gives you a good idea of what that function does. The last thing that we're going to cover today is just a brief preview of RMarkdown. It's really the preferred way of writing scripts. And it's a way of implementing literate programming where you can write plain text explanation of what it is that you're doing and what you're hoping to achieve, and also some results that you're observing once you make a figure. And as I said earlier, it's preferable to Jupyter Notebooks because it's easily version trackable. It can compile to HTML, PDF, Markdown, and Word, and it's a really great way of displaying and communicating your results to others. So what we've been using so far is just an R script. But in order to make an R Markdown, you can go up to this new file button and click R Markdown. It asks you for a title. We'll continue with our theme here and just say this is our first R Markdown. We can keep the default output format as HTML. And when it loads, we can see that there is already example text showing us the structure of an R Markdown document. At the top, there's 3 dashes followed by a title and an output. This is generally where some metadata for the document goes. And then inside each of these 3 backticks areas called chunks is where the R code goes. So all of the scripting that we've done here can just go into one of these R chunks, and we can run it just as we would a normal R script. It also allows us to write with Markdown formatting, which means that we can create headers by using just a £, and make things in bold or italics with some stars surrounding them. So the nifty thing is that once we save this document, we can knit it into an HTML using this knit button here. The first time you do this, it may ask you to install some packages. You can go ahead and do that. So once you hit knit, it will run all of the code, produce the figures, and create an HTML document out of that where the R Markdown is formatted according to Markdown syntax. And then all of your code is in these neat little gray boxes with the outputs below. So you can see this is a summary of everything that we've run today. Finally, I want to close out today just with some general data scripting principles. There's often a trade-off between generalizability and speed when you're writing code. So research code, or really sloppy code that is stream of consciousness, is a real thing. You want to generally err on the side of reproducibility and readability, but there's no need to over-polish your code until you're sure it'll be used in a figure or software. Also, you'll always want to do things in scripts so that you can save them easily and reproduce what you've done previously. Doing things one by one on the command line is not reproducible, and saving your session history will not help you later. Finally, make sure to track all your R scripts in a Git repository. Even though we didn't do that today, moving forward in class, we'll be tracking everything with Git. That's all for today. I know that was a lot, but these slides are there for reference, and you can rewatch this video at your leisure.